Now, in this lecture, I want to continue with our discussion on serverless web APIs. So the slides that I'm going to be working my way through are still in this deck here. And where we left off, you remember, we got to the stage where we used the CDK to provision a Lambda function. And then we invoked that Lambda function using the CLI. And I also showed you that if the Lambda has a console log statement or statements in it, then those log statements can be viewed using the CloudWatch service. So we'll pick it up from there. And in my slides, we're getting to here. Now, the title here is Lambda integration, but I'm not talking about integration here in terms of what your Lambda can do, because your Lambda function can communicate with any other AWS service. By Lambda integration here, I mean what services can trigger the execution of your Lambda. And this goes back to the kind of event sourcing idea, which the demonstration that I've just given you there doesn't have any illustration of event sourcing though. So it turns out that quite a number of the AWS services can potentially be the source of the events that trigger the execution of a Lambda function. And we'll see some of them in the next few weeks. Well, one in particular, I suppose, and we'll see others later on in this module. So I'm not going to go through the services that I mentioned here. Just suffice it to say that all of the services that I've mentioned here, some of them you're not familiar with, some of them you are. If you just take S3, for example, you can trigger the execution of a Lambda as a result of some state change in an S3 bucket. And I've kind of mentioned that already. But you've got to express that in your CDK code. And the CDK framework will take care of setting up the infrastructure to achieve that. So there's quite a number of services that can be the triggers for a Lambda function. The way it's modeled from a kind of an implementation point of view is you can have synchronous invocation of your Lambda function, an asynchronous invocation, or you can have what's called a polled-based invocation of your Lambda function. So there's three different models, and the various services that I'm mentioning up here, they are restricted to using one of the models, and this is all kind of prescribed by AWS. You can't do an alternative. So whichever service that you're using, you're using as the trigger for your Lambda function, you've got to look at that service's integration with Lambda and follow the particular programming model prescribed, whether that be synchronous, asynchronous, or poll-based. I'm going to talk about each of those briefly. We'll experience synchronous in the next week or two. And so for the synchronous, which is usually the more straightforward kind of model, really, for a synchronous invocation, the services that follow that model are well, if you invoke it from the CLI, which I've just done, so we were essentially using we're invoking the Lambda function, and the CLI waited until the Lambda executed and responded back. That's typical synchronous invocation. Also, if you want to write an application that's using an SDK, so for example, you could write a Python script or indeed a TypeScript script, run that TypeScript locally on your machine, and use the SDK to communicate with a Lambda function. But the communication is synchronous as well, because the particular application that you have written is going to wait for the response. API gateway follows this synchronous model. We'll look at API gateway next week, I think. You can actually link up a load balancer with a Lambda function. Doesn't always, Lambda load balancer isn't always the front for an EC2. So we won't be looking at that, but that is possible. But if you do integrate a load balancer with a Lambda function, the communication between the two is synchronous. And there's also something called function URLs, which I'll illustrate in a minute to you. You can actually get the Lambda service to generate a URL for your Lambda function, and then you can invoke it from a browser or some other type of web client. But the communication is synchronous as well. And, the picture here kind of demonstrates some of those. So if we're using the AWS CLI or the CDK, and we saw that there a moment ago, you invoke it, the Lambda executes and it responds back. If we're using API Gateway, which we will be doing next week, API Gateway is this serverless service for developing web APIs. But either way, your client, presumably your browser, sends a HTTP request to this API Gateway service. It communicates with the Lambda, and you have to, in the CDK code, you have to kind of set up this integration here. The Lambda executes, the response comes back, and the response is sent back to the client. But again, it's all synchronous. In the function URLs idea, you can actually invoke directly from a web client. You don't have to go through the API Gateway. You can have a web client that communicates directly with a Lambda if that Lambda function has a URL generated for it. So that's synchronous invocation. And let's see an example of that happening. And in this example, I'm going to use the same CDK application that I had there a moment ago, my single little Lambda, but I'm going to get the CDK to generate a URL for that Lambda, and that will allow me to invoke it from a browser or from Postman. In addition, you can actually configure the URL to be a private URL. And in that case, there has to be some form of authentication with the HTTP request to the Lambda function. So how do I get the CDK to generate a URL from my Lambda function? So I'm just going to, because I've prepared this earlier on, I'm going to check out, did I make any changes there? No, I'm going to check out this branch. Again, let's look at the CDK code. The Lambda itself hasn't changed. I don't think it's much the same as before. The CDK code. Okay, I create my Lambda instance as before, and this is how I just get it to generate a URL for me for the Lambda. And so I'm adding a function URL. That's okay. You can configure the URL to be public or private. Let's start off by making it public. So the authentication type would be none in this case. And you can also configure a CORS setting for our CORS configuration for your URL if you want to, but I'm not going to in this case. And I'm also getting my CDK stack to output the generated URL for me so that I can then just use it. So that's my stack. Let's redeploy. Okay, and let's see, here's the URL. So if I just click on it, then voila, I get my response. This is the response that was actually generated by my Lambda function. And let's confirm that that is still what the Lambda function generates. Yeah, it's the same. That's the, see, there's a text message that it generates, and that's what I get back in my browser. That looks good. If I now, let's say I want to make that URL. So I am triggering, what am I doing there? I'm triggering the Lambda via a URL that has been generated for it by the Lambda service. That ability to associate a URL with a Lambda, that's a fairly recent feature that was added to the AWS Lambda service. It's only been around since 2022, I think. Now, you can actually make that URL protected or private. And so, and the only form of authentication that's supported for private Lambda URLs is based on the IAM, authentication. In other words, SIG-v4, if you're familiar with SIG-v4 from last year. So to make my URL private, I need to just change the configuration slightly of the stack. As in here. You can see there are only two options available to me, either public or private based on the AWS IAM authentication model. Let's save that, redeploy. So it's all pretty straightforward so far, really. I think there's nothing too much too interesting happening. When we start getting into bringing a database into the equation and API gateway, then we'll have a richer, we'll have a set of Lambdas all sort of sitting behind an API gateway, and that will provide obviously more functionality. And we'll just get the Lambdas, most of them just interacting with a DynamoDB database. So again, it's fairly standard kind of stuff, admittedly. The theme though is it's all based on this kind of serverless model. So here's my URL in this case. But clicking on it now isn't going to work because it's a protected URL, but let's try it anyway. Okay, so I get a forbidden. So now I'm going to switch over and use Postman as a way of invoking this URL. And in my, so I'm going to set up a GET request, HTTP GET request to this particular URL, but I need to provide my AWS access key credentials, and Postman takes care of using those credentials to generate the relevant authentication headers and indeed some query string arguments, generating all of those and sending them with the GET request to the URL to the AWS Lambda service. The Lambda service checks the authentication credentials that have been passed to it, and then it will either allow it to execute the Lambda or not. So if I bring up Postman, now we will use Postman quite a lot in the first half of this module because it's going to allow us to test our serverless web API when we eventually get to develop those. But for this particular use case, what we do is create a new HTTP request. Kind of assuming you may have used Postman already, but some of you may not. So create a new HTTP request, which I've done. Give it a name, and then essentially fill out this part on the right. So if I grab the URL that was generated by the CDK for me, then select the Auth tab. And we need to select the authentication type, which in this case is AWS SIG-v4, which you'll find down here. And when you select that, then there are some fields that you need to fill out on the right-hand side. Now, the access key and the sort secret key, they are the keys that were generated for you when you created your IAM user. So you'll get those off your own local machine. And so I've pasted in my 2 keys into these entry points. And also, if you expand the advanced configuration, you also need to fill out the region, which in our case is EUS1, and just set the service to Lambda. The rest you can leave blank. And so what Postman will do is take those details and use them to create the relevant authentication headers and also a query string parameter. And now if I just click send, then the response that I'm getting back here, that is consistent with the response that my Lambda would have created, which is that. So that seemed to work okay, just to prove it that it doesn't work when it shouldn't, I guess. If we just kind of mess up the keys, so if I just make a small change to my key, either the access key or the secret key, save it, and then try and do a send. And I'm getting back an error message, which would be generated by the Lambda service itself, because it's the Lambda service that will perform the authentication check. That's the synchronous model. The asynchronous model I'm just going to talk about, but we won't demonstrate it because it's a bit more complex in terms of setting it up. The asynchronous model is relevant if you have, if you want to associate an S3 event as being the event source for triggering your Lambda, or if you're using a simple notification service, if you want that to trigger a Lambda and some other options as well. Like if we demonstrate the S3 one might be the easiest one to explain. The idea is somehow, some way you have access to an S3 bucket, and let's say we add an object to that bucket. We have our Lambda function over here, and we've configured the Lambda via our CDK in our case such that we want this lambda to be invoked whenever a new object is added to the bucket. When that eventually gets deployed, what the AWS service does is it generates a queue, and when the event occurs within the S3 bucket, the S3 service will communicate that event to the AWS service. The AWS service will know that event is associated with this lambda, and it will add the event itself to this queue. And there may be many of them, you know. So the events themselves are queued up in this structure here, which is all created behind the scenes for you by the AWS service as a result of our CDK code. And it invokes the lambda then. It triggers, the AWS service triggers the lambda to go and retrieve whatever events are in this queue. So what it actually will receive is a batch, or it could be a batch of just one, but it receives a batch of events that are linked to the S3 bucket, and it just processes them. But how is this model asynchronous? It's asynchronous because this is my client way over here, and my client is not waiting for the lambda function to process the events. All the client is doing is putting an object into the bucket, and then it's finished as far as it's concerned. The triggering of the lambda happens asynchronously behind the scenes between the S3 service and the AWS Lambda service via this kind of queuing mechanism that's managed for you by AWS itself. So the Lambda service up here, I'm saying the Lambda service places the events in a queue. The Lambda service, if for whatever reason, so it will invoke, it will trigger your Lambda, and the Lambda will process a batch of events from the queue. If for whatever reason the Lambda crashes, we needn't get into the details of why, then if the Lambda function crashes, then the Lambda service will actually retry the invocation, or it will re-invoke the Lambda again to try and complete the processing, and it does that 3 times. I think it's pre-configured to retry it 3 times. Eventually, it gives up on it, and we kind of have to deal with the consequences programmatically some way. But the Lambda service will take care of re-invoking your Lambda on a number of occasions to complete the processing. And because of that, you've got to make sure that I'm saying here that your Lambda implementation is idempotent, because what might happen is the Lambda gets invoked with a batch of 10 events. It processes the first 5 and then crashes, which means the Lambda service will re-invoke your Lambda function, gives it the batch of 10 again. Now you've got to make sure, because it's already processed the first 5, whatever the nature of that processing is, it needs to be idempotent, because it is actually going to process the first 5 all over again. So you've got to be aware of that, is all I'm saying. I'm saying here it does 3 retries using what's called a an exponential back-off algorithm. All I mean by that is that the second execution, it will delay the second invocation for a period, let's say 3 seconds. If the Lambda still crashes, then the Lambda service will delay for double that, 6 seconds, and then tries again. If it still crashes on this second occasion, it will wait for double the delay time, which we're now up to 12 seconds, and then invoke it again. And now we've had 3 retries At that stage, it gives up. And we can talk some other time about how we clean up all of this stuff. But the Lambda service takes care of retrying your Lambda function on a number of occasions in case of failure. Why would we take this approach at all? Like, you might ask, why not have a Lambda here so that the client sends the object to your Lambda function processes it, and then puts it into the bucket? That would be a synchronous approach, because now our client, because it's invoking the Lambda directly, our client is waiting for the Lambda to do the processing and put it into the bucket. Whereas in the asynchronous model, all it's doing is just put the object into the bucket and it's finished. And the reason you might take this asynchronous approach is because, well, maybe the client doesn't really need to care, doesn't care about whether the processing has been completed or not. All it cares about is, has the object been added to the bucket? The client doesn't have to wait for all the processing to happen. And that means our client-side application there's a faster response to the end user as a result. Okay, all of the processing hasn't been completed, so the end user can say, just because they got a response back, that all of the processing has been completed. But there are occasions when this asynchronous model is suitable. So we've got the synchronous model, we've got the asynchronous model, and the third option is this event source mapping model, which is kind of odd, kind of an odd one out, but it's there for technical reasons. We don't need to, nor have I studied in detail the technical reasons for it. But the way this third model is implemented, and it applies if you're using what are called DynamoDB streams. So the idea here is your client is, let's say, updating this DynamoDB database, which it's just an ordinary database as far as we're concerned. It's adding records, it's modifying records. And we want a particular Lambda function to carry out some processing as a result of some change to the database. Again, we don't have to go into detail of what the nature of the processing is, but we want to trigger a piece of functionality every time there is a change in my database state, as in new record added, record has been deleted, record has been updated. So that's the event that I want to trigger my Lambda function, the change within my Dynamo database. And so the way it works, again, from a CDK point of view, you provision the Lambda function, you provision the DynamoDB database, and you express the fact that you want this Lambda to be triggered by the state change in the database. And then the AWS service sets up this kind of infrastructure. And the way it works in this case is it works on a polling basis. The AWS service periodically asks the database, have you experienced a state change since I polled you the previous time? And there may be a number of state changes between two consecutive pollings. So the AWS service does that polling for you. If there have been a number of state changes, by the way, every time there is a state change in my DynamoDB database, that state change is logged internally by DynamoDB. And we refer to that log as a stream. And so when the AWS service polls the DynamoDB database, it essentially gives that stream of logs as the response. That stream is put into this intermediate queue, and yet again, the Lambda service is provided with the contents of that queue as a batch of events, and it processes them again. But the key point here is that the AWS service is polling my event source for events, whereas in the asynchronous model, if I just quickly go back to it, in this model, the event source is telling the AWS service about the events. It's providing the events to it. And okay, the AWS service puts them into the queue. So there's a different kind of invocation sequence going on between this asynchronous model and the event sourcing model. This event sourcing idea is also used by SQS, which is a service that we'll use later on. It's also used by Kinesis streams, which we won't use. So we will see later on an example of where we can set up a Lambda that's triggered by a DynamoDB database state change. Now, the Lambda service, in fact, pretty much all of the services, they provide an API interface so that other services can communicate with them. And this is the case with Lambda. So that's what I'm trying to represent in my picture here. I've got my Lambda service. And it has an API interface. And that's what we use. So for example, when we were using the CDK to talk to our Lambda function, our CDK communicated via the API to the actual Lambda. So in effect, it's asking the API service to send an event to a particular Lambda. And the same applies for any other service that will want to talk to a Lambda. So our S3 bucket case, it's using the API provided by the Lambda service as well. Now, this API, essentially it's just a HTTP interface, although strictly speaking, it's a HTTPS interface. So these are all kind of network calls that are being made here. Now, in terms of on the client side, you don't want to be making raw network calls. And so for that reason, the API that the service provides, there is an SDK provided by the AWS service that just makes the invocation programmatic rather than having to make HTTP calls. So that's what I'm trying to get across here, that each of these services that are trying to invoke a particular Lambda function, they're using the AWS SDK package to facilitate the communication. And so if we wanted to write our own piece of code to communicate with a Lambda function, we would use the AWS SDK as well. And that's irrespective of whether it's the synchronous or the asynchronous programming model. I'm saying here you can pass any type of event, any type of payload can be passed to a Lambda function. It's up to the Lambda function on the extreme right then to parse it and interpret it. But there's no kind of formal structure for the event. It can be anything. Hence, anything can trigger a Lambda function. But for the purpose of this diagram, anyway, all I'm saying is that all communications to your Lambda function, it all goes through this API that's provided by the Lambda service. So it's in control of it. By the way, even though it's not significant to us, your Lambdas are not running inside your VPC. They're actually running outside of VPC. You can have it such that your Lambdas are running inside a particular VPC. It's obviously more secure, but it's a little bit trickier to set that up. And I conveniently kind of avoid that in any of the stuff that I do with you. So just be aware of the fact that Lambdas by default run outside of any VPC kind of context. Now, so far our Lambda functions that we've developed in the labs, they don't really do anything other than they maybe issue a console.log to CloudWatch. But even that though, even though like by default, a Lambda function cannot communicate with any other service. This is typical AWS stuff, right? It's big on security. So you have to be explicit about what services your Lambda function can interact with. Now, even though our Lambda function did a console.log and that's all it did, we still have to give the Lambda function the permission to talk to CloudWatch logs. So a Lambda, every Lambda has what's called an execution role. So you have to actually define an IAM role and associate that IAM role with the Lambda function. And we refer to that as the execution role for your Lambda. Now, conveniently, that's done behind the scenes for us by the CDK. But if we didn't have the CDK and we had to write all of our infrastructure as code using CloudFormation templating, then we would have to create IAM roles and associate policies with those roles and then attach the role to our Lambda function so that our Lambda actually works. But CDK does that kind of behind the scenes for us. So number one, anyway, this idea of a Lambda execution role, what its purpose is, it grants the Lambda function permission to access other services. There are lots of, and we know the way IAM is kind of structured. We talk about roles and policies and permissions, and you attach a policy to a role, and the policy kind of states what permissions are associated with that role. You're kind of familiar with all that stuff from the DevOps module. There are a number of predefined policies that the AWS people created for us just for convenience. So we call these managed policies. So there are lots of managed policies specifically related to the Lambda service. And I'm just mentioning some of them here, just kind of randomly. Although the very first one, AWS Lambda basic execution role, every Lambda function has to have this particular role associated with it. Otherwise, it wouldn't be able to talk to CloudWatch logs. Because if you looked at the detail behind this particular role, you would see that that is what it enables. It enables the possessor of the role, if you like, our Lambda function. It allows it the right to send logs to the CloudWatch service. Another example, SQS. Okay, if your Lambda wants to put messages into SQS, then there's this predefined managed policy, and so on and so forth. Right. If we just switch over to the management console for a moment, and if I go into the Lambda service, now this is the Lambda function that was created by the CDK for my little demo app with the function URLs. So if I just follow through, click on that, and here's some details on the Lambda function. And if we go down to the configuration tab, and then select permissions, you can see here I have some details on the execution role for this Lambda function. And the role itself, as I said, was auto-generated by the CDK for this Lambda, and specifically for this Lambda function. You can see from the drop-down menu here the set of services that my Lambda uses. Now, there's only one entry on it because it only uses CloudWatch logs. But if I follow through and on the role click through, then it brings me into the IAM section, or the IAM service, because that's the service that manages all of the security stuff. And if we drill down into this role and look at the permissions, so here we can see that there is one policy attached to this role, and it's one of the managed policies that I mentioned there a while ago. It's the one that it's the kind of basic policy that's associated with any Lambda function to allow it to talk to CloudWatch logs. So this is an example of a managed policy. And if I click through that to see the details of that policy, and these policies are, as you may know, are written in JSON. You can write your own custom policies, and we'll see how you do that using the CDK a little bit later on. But if we try and find the detail behind this policy, let's see, how can I do that? Yeah, if we look at the JSON here, as I said, we write these policies in raw form in JSON, but this is essentially telling me that this policy allows the entity that has this policy, our Lambda function in our case, can interact with CloudWatch. It can create CloudWatch groups, CloudWatch log streams, and it can also write to a log stream. So that's all of what's going on kind of behind the scenes. That's fine. The slight complication is there's also this thing called the resource-based policies associated with a Lambda. It's not that complicated, actually, when you think about it. The resource-based policies, they dictate who can invoke your Lambda. The execution policy dictate what your Lambda can talk to or interact with. The resource-based policy controls who can invoke your Lambda, whether the who be another service or an actual another user or another account, AWS account other than your own account. So for if you talk about another IAM principal, an IAM principal is another user. Another user can invoke a Lambda that's contained within your account if that other user has an IAM policy that grants that, or if the Lambda's resource-based policy grants it. And we're specifically interested in the resource-based policy approach. Unfortunately, again, a lot of this stuff is at the lower level anyway, is taken care of for us by the CDK based on certain instructions that we provide in the infrastructure code. So it's generating another set of policies. I was showing you a policy there a moment ago that was linked to the execution role. It also generates policies linked to the resource-based policy side of a Lambda. Right, and we will see these. It doesn't really apply to the Lambdas that we're writing so far because we're actually invoking them directly using a URL. But when we start talking about, for example, API Gateway, then API Gateway is just another service which can invoke a Lambda. And for that service to be able to invoke your Lambda, you've got to specify, or it has to be specified in that Lambda's resource-based policy that the API Gateway is allowed to do that. And we can come back to look at that maybe when it's relevant, but just for now, maybe if I just go back to the Lambda service. Here we are. Are we in the Lambda service? Are we there? No, one more tab. Okay, and if we in the configuration part, so I was talking about the execution role, but if we scroll further down, you can see there's a section here called resource-based policy as well. Okay, so I'm not going to delve into that today because we don't need to. So there's a lot of security stuff wrapped around Lambda that needs to be taken care of, all based on the IAM service, as everything related to security in AWS is centered around IAM. Now, when I started talking about Lambda last week, I said that it scales automatically based on usage, as in the more traffic that is hitting your Lambda, it scales up. And then when that traffic starts to decrease, then it scales back down again. So the little picture here is kind of illustrating that. So let's supposing I've got this Lambda function, and let's say there are two concurrent requests targeting this particular Lambda function. And because there are two concurrent requests, what the AWS Lambda service will do is it will create two instances of the Lambda, as in it will spin up two micro VM instances, load both of those instances with your Lambda code, and execute them in parallel, and send one request to one of the instances, and the other concurrent request to the other micro VM instance. On the right then, so that really just keeps on scaling. If you've got very high volume traffic, then the Lambda service just keeps on spinning up instances, micro VM instances, and loads your Lambda into them. So you could have lots and lots of instances running concurrently. Now, there is a limit though, and the limit that the AWS people arbitrarily decided was any AWS account cannot have more than 1,000 Lambda instances running concurrently, whether that be all of the same Lambda or of different Lambdas. Your total number of Lambda instances running at any particular point in time cannot exceed this upper limit of 1,000. That's just a decision that they made. You can actually request that the limit be increased. You can make a special request to the AWS, and this would be a fairly standard thing for large organizations, but certainly not in our case. Now, you can, though, I'm saying here, you can set what's called a reserved concurrency limit for any Lambda in any one of your applications. So rather than the potential of a particular Lambda within one of your applications getting up to this 1,000 figure, you can actually set an upper limit of whatever, let's say 10. And if there are 11 concurrent entries, if there are 11 concurrent requests hitting your particular Lambda, for which you have set a reserved concurrency limit of 10, then the 11th one is going to receive what's called a throttling error response. And that's a 429 status, HTTP 429 status code. That's called the throttling error code. And so if the client receives, if the client that's sending the request to your Lambda, or that's trying to trigger your Lambda, and let's supposing for simplicity's sake, it's just a client that we have written rather than another AWS service. If our client receives a 429 throttling error, then the advice is that the client should delay for a period, let's say 2 seconds, and then try and make the invocation again. In the intervening time, the concurrency limit might have, the number of concurrent instances of the Lambda that you're targeting might have decreased, and so your request is processed. But let's supposing it isn't. After 2 seconds, it's not processed. You get a throttling error again. Then the advice is that you double the delay period. So we're up to 4 seconds now. Try again. If it fails again, double it again, and keep on going. Well, not keep on going, but maybe 3 or 4 iterations of that approach. So you're doubling the delay period between sequential attempts to invoke your Lambda. That's referred to as the exponential back-off algorithm approach towards dealing with throttling errors from the client's point of view. So a limit of 1,000, but you're advised maybe to set, it's a good idea to set a reservation or reserved concurrency limit on individual lambdas, and I'll explain why in a moment in the next slide. And that's just something that you would do at the CDK level in our case. It's just another option when we're configuring our lambdas in our CDK code. Okay, I've got that and I've gotten that. Yeah. Now, here's an explanation as to why it's probably a good idea to set, in general, to set reserved concurrency limits on lambdas. So what I'm trying to get across here, let's supposing I've got 3 different applications all running in my AWS account. The specifics aren't that important, but just to explain them. So it looks like this application up here, it has an application load balancer. It's getting very high traffic hitting it. And by the way, an application load balancer can issue requests to invoke lambdas. We're not doing it, but it can be done. So it looks like this application here is actually spinning up very high volumes of concurrent lambda instances. And let's supposing it's currently at 1,000, right? So it's reached my AWS account's upper limit for the number of concurrent lambda instances that can be that it can tolerate. But I've got another application also running in my account, and just by the way, this other application it has an API gateway, which we're not too interested in. But this other application, even though there's only one user trying to access it, this user is going to get a throttling error response back, okay, because the 1,000 limit now has been consumed by this first application. And even if I've got a third application, which can be invoked from the CLI, let's say, that's also going to get a throttling error for the same reason. So in other words, the first application on the top, it's essentially kind of hogging the concurrency limit that has been set by AWS. However, if we actually set a reserve limit for whatever this lambda is, if we set a reserve limit of, let's say, 100 on it, then these other 2 applications are not going to get throttling errors. And that's probably, obviously it's a balancing act, but it's probably a good idea to set some sort of reserved concurrency limit for this application because of its the nature, whatever the nature of it is. I talked about, well, I didn't talk about it that much maybe, but I did mention this notion of cold starts and warm starts for your Lambda function. So again, the way a Lambda execution works is when whatever event that triggers the Lambda, when that event occurs, the AWS service creates or it provisions a micro VM instance. It loads your code into that micro VM, and it executes the initialization code, and it then executes the handler within the Lambda. We refer to that as a cold start of our Lambda function. Cold because it had to execute the initialization code. That initialization code, you know, it can be lengthy. It can be time consuming. You know, if in the initialization code, which is typically the case, you are trying to form connections with other services, like let's say you're trying to get a connection to a DynamoDB table. So it is significant from a latency point of view, consumes a lot of time. And just to finish the story, if you remember, so the warm start idea is So let's supposing the Lambda service has spinned up a micro VM instance, loaded our Lambda code into it, executed the initialization code, and then executed the handler, and everything went fine. Let's say another request comes in, not a concurrent one now, because if it's a concurrent one, it's just going to spin up another VM and go through the same cold start process. But another request comes in after the first request has been processed, then provided the subsequent request is sometime in the immediate kind of future, and not being specific about time-wise now, but the Lambda service will reuse the micro VM that it has already spun up to handle the first request. But in this second case, it does not execute the initialization code, because any any connections that were formed are still there. In the second case, it's only going to execute the handler function itself. It's not going to run the initialization code. And so that is referred to as a warm start for the processing of that second event. But there's a significant time difference between the cold and the warm, obviously. How can you avoid these cold starts? Because they can be significant, okay? How can you avoid them? Well, there is this thing called provision concurrency, which is different now from reserved concurrency. Provision concurrency, essentially the idea is, and again, you would express the option to have provision concurrency in your infrastructure code. The idea is that the Lambda service will actually spin up a couple of micro VM instances, load your code into those instances, and run the initialization code. It will do that even though no requests have been made to your Lambda function. In other words, it's kind of provisioning some VM instances with your code ready to receive requests. So again, that's probably something that in real life production environments you would think about. Maybe should you set a provisioned concurrency value for particular lambdas within your suite of lambdas within an application, and presumably you would decide on setting a provision concurrency if the initialization code was quite lengthy in terms of the processing that it had to do. So it's just another configuration option. We won't necessarily be going into this kind of fine-tuning. I'm just making you aware of these configuration settings. Now, there's lots of other aspects of the Lambda service that we could look at, but I'm deciding to stop here and start looking at other serverless services. Although it's worth saying that for the entire remainder of this module, we will be writing lots and lots of Lambda code, where our Lambdas will be talking to other services, and our Lambdas will be triggered by other services. So that is going to be a big part of the rest of this module. But for now, we'll just park Lambda. And I want to talk about another serverless service, and the one that we've mentioned a number of times already, DynamoDB. Now, I did say to you, I think I said to you the last day, this is not a database module, so I'm not going to get into a lot of the DynamoDB stuff that we could look at. I'm just going to cover the basics that we need in order to be able to create some DynamoDB tables and have our Lambda talking to them. We won't necessarily, I've no problem admitting that we won't necessarily be following best practice in the design of our DynamoDB tables, okay? But I'm not too concerned about that because, again, as I said, it's not a major focus for this module. So what is DynamoDB? It's a non-relational or NoSQL database. So that kind of means it's a bit like MongoDB from your studies last year. The second point I'm saying on the slide is that it's a fully managed. Whenever you see the term of the term fully managed, straight away, that is a byword for serverless. So it's a fully managed I'm saying it's a highly available with replication across 3 AZ zones. So when you create a DynamoDB table, behind the scenes, the DynamoDB service makes 3 copies of that table across 3 different availability zones. And that is the point, the purpose of that is to guarantee the availability of your data to whoever is trying to access it or whatever is trying to access it. And again, you kind of get that for free, if you like. So that's how they approach the high availability target for DynamoDB. I'm saying it's schemaless. Essentially, you can have records with completely different structures all inside the one table. And in fact, that's encouraged. And I'm not going to go into why, but it is it's this schemaless nature that's built into DynamoDB. Okay, every record in a table has to have a primary key, and the type of the primary key has to be the same. But apart from the primary key, every other part of a record, its structure can differ from one record to the next. Okay, it scales automatically. I'll come back to that in a little while, but it does just scale up in size for free. And it's actually built into the way it's designed behind the scenes, and I'll give you a slight insight to that a little bit later on. It uses IAM behind the scenes for any kind of security issues, and that's again just it's consistent across all aspects of AWS best practice, which is use IAM to secure things. Okay, it enables event-driven processing. That's kind of a link back to what I was talking about earlier on, where we had our DynamoDB streams and all of that. Okay, that comes under this kind of heading of event-driven programming. Now, every kind of technology has its own terms, and same is true of DynamoDB. So in DynamoDB, okay, we talk about it's made up of tables. Well, that's a term we're familiar with from relational database world. Each table has a primary key, which must be unique. That's fine. The term primary key is familiar to us from other database stuff that you've studied. What I'm saying here is that you have to declare at the outset what the primary key is, and that kind of makes sense, I guess. Each table has an infinite number of items. Now, we use this term item instead of row or record in the DynamoDB world. So a table is made up of items is the correct way of kind of describing things. The next line is saying each item has attributes. The attributes are kind of columns, if you like, but I've already said that that DynamoDB is schemaless, so the attributes for one record might be completely different for the attributes for another record, and DynamoDB doesn't complain about that. Obviously, you have to be aware of that when you're interacting with it, but the DynamoDB service itself, it doesn't force you to have a structure for each item in a table. The maximum size of an item is 400 kilobytes. Okay, that's probably sufficient for one item stroke record. The data types of the attributes are, what you'd expect. So an attribute might be a string or a number or a binary value, but there are these other types as well, which we won't necessarily need to use, but you can have a list type and a map type. That's a particular attribute now. Could be a list of things, or it could be a map structure. Or you have this set type. So a particular attribute might be a set of strings or a set of numbers. So that's all possible. So if you like, these types here are native to, even though they're native to DynamoDB. So I said every DynamoDB table has to have a primary key, and there are 2 structures for the primary key. or two options as to the design, if you like, of the primary key. Option one is where the primary key is just a single value. And we refer to that as being the partition key. Can be a little bit confusing, the use of primary key and partition key, but if your primary key is a single value, then we tend to refer to that as the partition key of your table, and the partition key of the item in the table tends to be some sort of hash value. We're told that the partition key has to be unique. That's kind of the same for primary key, isn't it? It has to be unique, but also its range of values has to be diverse. It has to have a very wide value range. That is significant now, but that nearly applies in most cases anyway. And okay, the example is one we work out ourselves. So we've got a table of user records, well, user items, then the user's ID would be an appropriate choice for your primary key stroke partition key. Nothing terribly new there, actually. Option two is where the primary key is a compound or composite key. And in that case, it's comprised of our partition key. So you always have to decide what is the partition key attribute of the items in a table. But as well, your primary key in the second case has what's called a sort key part to it. So in this option two, you could have more than one item in a table that has the same partition key, but it has a different sort key. And then the sort key and partition key combination, though, that does have to be unique, which I'm saying here. We talk about collections in this second case. So if you can kind of visualize, and I probably have a picture a little bit later on. In fact, there's a picture here on the right. Okay, let's supposing we've got this gaming application, and we've got lots of users that play our online games, and we've got a small set of games, let's say, or a smaller set of games, but we've got a large user base, and we want to store, let's say, each user's score for a particular game, and maybe some other attributes as well associated with a user having played a game. And okay, so for that table, then we could, because a user can play many different games, the user ID is going to be our partition key, because that satisfies the criteria for a partition key, i.e., it has a wide, diverse range of values. But because a user can play multiple games, then we're going to have multiple records or items in our table for a particular user. So the partition key or the user ID on its own is not going to be sufficient for a primary key. We need a second part to add to that to make up a primary key. And I've decided that the game ID, that can be the sort key in this approach up here. So the sort key is the game ID, the user ID is the partition key, and that combination is the primary key. This combination here is the primary key for this table. And it's guaranteed to be unique, as in, well, we're assuming a user doesn't play a game twice. And even if they do, we just store a different result for them. Okay, but that combination will only occur once in our table. So the terms here are partition key, sort key, and that's about it really, and primary key. And the primary key is either just a single value, in which case it doubles up with the notion of a partition key, or the primary key is a composite or compound key, in which case it's made up of a partition key and a sort key. Now, I'll talk about what the significance of the partition key is, because that affects where your data is stored. I'll do that in a slide or two. In terms of CDK, how do we create a Dynamo? We don't create a DynamoDB database. What we do is create a DynamoDB table. So an application may comprise of a number of tables, and you just create them separately using your CDK code. And you've done this in the labs this week. So this looks kind of familiar to us. Here we're creating a DynamoDB table. We're linking it to the current stack that this code is contained in. This is just a CDK, if you like, kind of identifier for this construct. Remember, I talked about when I talked about CDK initially, I talked about L1 constructs, L2 constructs, and L3 constructs. Strictly speaking, this is an L2 construct. And so we've got to give the resource associated with that construct some sort of an identifier. That's okay. And the rest then is our configuration for this table. Don't worry about the billing, the billing mode. We're always going to set it to this. Here we are, partition key. So we have to, I did say in the slides that we have to declare the partition key at creation time. And here I'm saying that my partition key, the name of the partition key is going to be movie ID and its type is number. And the rest then, the removal policy, what that controls is when you just destroy your stack, do you want the table to be destroyed as well? Now, in a production environment, you probably do not. You would like the table to remain even when you destroy the stack that it's associated with it. You may or may not. Okay, but certainly in a development environment, it's probably a good idea to have the table destroyed whenever the stack is destroyed. And that's what I'm requesting here. And the table name then is just the table name within the DynamoDB world, if you like. On the bottom, then I'm showing you what the management console interface looks like for DynamoDB. And you would have played with that a little bit in the labs. But if I just very quickly jump over to DynamoDB, because I've already deployed the app that you will be completing next week. Well, in fact, the app already has the work that you've done this week already has a DynamoDB table. So you're probably already familiar with this, but we'll go in anyway. And so you have independent tables. Now I only have one at the moment. The tables, could be linked to different applications. They're just kind of standalone, if you like. Go into a table, typically something that you might want to do when you're playing around with DynamoDB initially is you want to see the data inside in the table, or you want to see, is there data in there? Or maybe if you've got a Lambda function that adds an item to a table, then you'd like to confirm that it's in there. So the way you would do that is if you select over here, explore table, or you can, if there's a lot of data, you can restrict how much data it shows. But if you scroll down, we can see here, these are the actual items, the movie items that we put into our table as part of our seeding. So we're kind of happy now that they're in there. And of course, you can delete items here. You can add items from this management console, but we don't like taking that kind of manual approach. Other than that, for now anyway, we don't need to look at any of these other options over here. Now, it does turn out, as we look at it, this one, the schemaless nature of DynamoDB isn't really illustrated here because every single record has the exact same structure. But, and to be honest, we won't get into a situation where we will want to leverage that schemaless idea. But it is a pretty important part of DynamoDB, as it turns out. horizontal scaling, the very first slide I had there on DynamoDB, I think I mentioned, or I might have just mentioned it's in passing, that DynamoDB scales automatically. Scaling here relates to just growing the size of your table. That's what we mean by scaling. And it scales, I'm saying, horizontally. So when you create a table, the data is actually distributed across a fleet. I'm saying the very first point here, it's distributed across a fleet of computers. So it's automatically partitioned. The actual content of a table is distributed across a fleet of computers. And each computer stores one partition of your overall table structure, if you like. And okay, the partition size can be up to 10 gigabytes. So we're thinking in terms of large scale databases now, obviously. And the advantage, so why did they decide to do that? Well, sorry, before I decide, it's really got to do with performance. So what's the consequence of that? Well, let's supposing here I've got this table and it's actually split over 4 partitions. I'm needing to get into why they decide on 4 partitions as opposed to 3 or whatever, but it's split over 4 partitions. So DynamoDB this is my DynamoDB service logo, okay, and it's managing the interaction with this particular table. So let's supposing the DynamoDB service receives a put item request. Put item is essentially, I want to add an item to my table. And let's supposing we're dealing with our gaming application where we want to add a record storing or recording a user's score and other data associated with a user playing a particular game in our gaming application. And we decided a few slides back that that table, its primary key is a combination of a partition key, which we chose user ID to be the partition key, and a sort key. And we decided that the game ID would be the sort key. The important one here, though, is the user ID. We've decided that that is the partition key for this particular cable. So when the DynamoDB service receives a put item request, as in add a new item to a table, and we're giving it the partition key and sort key and the other attributes, then what the service does is it puts that partition key through an algorithm, and the algorithm decides which partition the item should be stored in. And it obviously is trying to distribute the data evenly across our 4 partitions. Equally, if our service receives a get item request where we want to read a particular record, and when you do issue a get item request to DynamoDB, you have to give it the full primary key as you would for any other database. So in the context of this example, we would have to specify the user ID and the game ID of the item that we're interested in. And in the same way, the DynamoDB service will take the partition key part of the primary key, put that through with the algorithm, which will return with the relevant partition that should be queried for the record. And then the DynamoDB service goes to that partition or makes the request to that particular partition, i.e. to that particular computer for the particular item. And so by spreading the data across multiple partitions, the DynamoDB service guarantees a certain performance limits, if you like, or it guarantees certain minimal latency in the response to any requests, whether the request be a get request or a put request, a read or a write, in other words. So the partition key that you choose is significant. It determines what partition a a record is stored in. And I did say that whatever attribute that you decide to be the partition key, its range of values should be diverse, because if they're not diverse, then that means that everything might go to one particular partition, and we don't want that. We want to spread it out as evenly as possible across a range of partitions. You don't have to worry about the algorithm that's provided by DynamoDB. All you've got to ensure as the designer is the diverse range of values for the attribute that you decide to be the partition key of your table. I didn't mention there, but what this means is that if you've got a table that has a composite primary key, i.e. a combination of a partition key and a sort key, then all of the items let's stick with the example, all of the items for a particular user, they are going to be stored in the same partition. And so all of the game results for a particular user will be in one partition. And that's what we want, because more than likely we're going to be querying for a collection of records associated with a particular user. And that group of records that all relate to one user, we refer to that, or DynamoDB refers to that as a collection, an item collection. If I just go back for a couple of slides, I think I might have skipped over it really. Where did I mention it? I mentioned it here, right? This notion of an item collection. And the items are grouped by partition key, which I was saying there a moment ago. They're all of the items with the same partition key, but a different sort key. They'll all be stored in a group on the same physical partition. And what it also means is that if you request that group of that collection, then you're guaranteed that they will be returned back to the client in the order based on what type of your sort key is. Now, when we were talking about the Lambda service, I mentioned that it provided an API interface, a RESTful API interface, with an accompanying SDK, and that facilitated other services communicating with Lambda. And the same is true of DynamoDB. It also has a RESTful API interface, and it has an accompanying SDK. So in the diagram I'm showing you there, that on the left, typically we have a Lambda function which wants to interact with DynamoDB. And so the Lambda function will use the DynamoDB SDK to facilitate sending requests to the DynamoDB service for the purpose of extracting or items from a table or adding items to a table. Now, just at a technical level, to communicate with the DynamoDB service, your client or Lambda function in our case needs to create an instance of a DynamoDB client. And it turns out that there are 3 types of clients provided by the SDK. There's kind of a low-level one, which is this one here, DynamoDB client. There's this DynamoDB client, which is sort of a low-level client class. The DynamoDB stream is for that streaming scenario that I was talking about a while back. So we won't be using that as such. And then thirdly, there's this long-winded one called DynamoDB document client. Now, it turns out that's the one that we will use most often because it's a higher level abstraction and just makes our programming model a little bit easier. Although the DynamoDB document client uses the low-level DynamoDB client internally, and we'll see that from the programming excerpts that we'll look at. At the bottom of this screen, I'm just showing you an excerpt from the package.json. And you can see it's the I'm including the SDK. It turns out that the SDK is broken up into a number of packages, and we're just using some of the packages in our sample applications, but they're all coming from the DynamoDB SDK as such. Right, so we have that SDK class as a way of communicating with DynamoDB. Turns out that there are 3 types of actions that you may want to carry out with DynamoDB. The first classification is single item requests, where you're either trying to get a single item or write a single item or update an item or delete an item. But it's a single item that you're dealing with. And obviously, if you're trying to carry out a single item action, then you need to specify the full primary key of that item. Otherwise, DynamoDB doesn't know which particular item it should return back to you, or update or delete, whatever the nature of the action is. The second type of action is what's called the query action. And this is where you want to read a range of items. And the range there is important because range actually relates to the sort key. Turns out you can only query a DynamoDB database based on the partition key and the sort key. You cannot query on other criteria. That may seem very limiting, but that's the constraint you have to live with. So when we talk about querying, we're talking about getting a collection of items, either the full collection. Remember, I used that word collection a few moments ago in relation to our sort key and partition key. You want a collection of items to either read or update, I guess, or delete maybe potentially. And so for these query type actions, query requests, in other words, it only applies, these query actions only apply for tables that have composite primary keys. Doesn't make sense if our table has a simple primary key, where the idea of a simple primary key is that the primary key just consists of the partition key. You cannot query a table whose primary key is just a partition key. There are other ways around it, obviously, but you can't use this query approach towards those types of tables. And so the query result items are always from the same partition. Okay, that is true, right? The results that you get back from a query request, they're all going to be coming from the same partition, as in, the things on the right there. They're going to be coming from one partition, because essentially, you see, what you'll be querying is, if we stick with our gaming application, you might be interested in all of the items for a particular user. Okay, that's all of the game's records that associated with a particular user. And we know that they are all going to be stored in the one partition based on the way the DynamoDB works. The third type of action is a scan, and the scan is the most inefficient one, because essentially a scan is saying, I want to read all the records, or I want to do something with all of the, I keep using the word records there, but I want to, it's mainly a read operation, really. I want to read all of the items from a particular table. And obviously that's quite a slow operation for DynamoDB to complete, because it has to request the items from each partition, which is from each computer, because the partition is linked with a separate computer. What I should also say about DynamoDB is that DynamoDB only supports eventual consistency. It does not support ACID consistency. anyway, a scan operation is where you're essentially scanning the entire set of partitions and to get all of the records, essentially all of the items from a particular table. Now, clearly, maybe once you've retrieved all of the items from a particular table, the client may want to reduce the result to some subset of those items, but the reduction is carried out on the client side. DynamoDB can't do any kind of fancy filtering of the items on the server side, on the DynamoDB side. You have to do the filtering. So there are constraints in terms of how you can certainly read from a DynamoDB database. Now, what are we looking at here? Let me see, sorry. Oh, yeah. Okay, so what I'm showing you here is how you interact with DynamoDB. And we're just doing simple reads for now. And this is, I think this code excerpt is taken from the lab that you started this week, but if I just take it from the top down, so we're doing a few imports. So essentially, we're importing the clients, the SDK classes that I was talking about there a few moments ago. There are kind of clients for talking to DynamoDB. Here, I'm just making essentially a connection. I'm trying to get a connection to a particular. Sorry, just give me 1 second. Okay, I'm just creating an instance of the DynamoDB class. If I just go back, I'm essentially creating, just erase that. I'm creating an instance of this guy. For a particular region, that's fine. Process.env there. This code I'm showing you here now is just extracted from a Lambda function, okay? And this bit here would be what we would call initialization code. This is what we would do as part of a cold start. And you haven't done it so far, but you can pass in environment variables into a Lambda function. And all I'm doing here is accessing a particular environment variable. So I'm passing in a region, looks like an AWS region string into it. And so we're trying to get a connection with the DynamoDB service for a particular region. That's okay. I haven't specified any table yet. On the next line, what I'm doing is I'm creating the other type of client. Again, if I can go back, I'm creating an instance of this guy, because this is the one that I really want to use to talk to DynamoDB. I don't want to use this one necessarily. I can, but if I use this one, then I've got to, it's much more low level, and I've got to provide a lot more parameters to it in order to complete my action, whether that be, a single item action, a query action, or a scan action. This one is much better. But in order to create an instance of that second client, the long-winded one, DynamoDB document client, I have to have an instance of this one first. Okay, so that's essentially what I'm doing here, right? I'm creating an instance of the high-level client. I'll just call it the document client. That's the term we use. We talk about the document client and the DynamoDB client. It sounds as if they're the same thing, but they're just slightly different from a coding point of view. So I have my document client, my here instance. And in terms of configuring your document client, you've got to provide it with an instance of the low-level client. That's what this is. Okay, that's referring just to this variable up here. You've also got to specify the marshalling and unmarshalling options. I'll come back to that in a minute. So we now have an instance of a document client, and we can now talk to the DynamoDB service for a particular region. How do I then let's say, how do I request, make a read request to on a particular table. Now, the way the document client is designed, you have to pass it what's called a command object. And here I am creating an instance of one particular type of command object, the get command object, which you would nearly guess is the command object that you would use if you want to do a read operation, and specifically a read of a single item from a particular table. So I'm creating an instance of this get command object, and I'm essentially passing that to my document client. That's the only parameter I'm passing to it. And I'm invoking, this is probably the only method of the document client that we use, the send method. And it's this idea that we're now sending a request to our DynamoDB service. And of course, that's happening across a network, which is why I'm prefacing it with the await. It's not local to me. Going back to my command object, for the get command object specifically, you have to pass it, you have to kind of configure it. You've got to tell it, well, what table am I querying? And that's where the table comes in. Again, I'm passing in table. This is, again, this code, let's say, is part of a Lambda function, and I'm passing in some environment variables into the Lambda function. And one of the environment variables I'm passing it in is the name of a table. So that's all this will equate to. And it's a single item request, so I have to give it the full primary key of my table. And we saw the creation of it's our movies example again, and we saw from a slide or two back that our movies table, its primary key was a single value, which was a partition key. It didn't have a sort key. So the key in this case, the primary key, is just going to be a single value. And I'm specifying that it's where I want the movie ID to be 1, 2, 3, 4. Movie ID here has to correspond to, if I go back, whatever you said it was here. So you've got to be careful about that. And so that's this example here is just how we programmatically interact with DynamoDB, and we're using the DynamoDB SDK to do that, as opposed to making raw HTTP calls within our Lambda code. I said up here that we have to also specify marshalling and unmarshalling options. And if I explain that using, let's say, this as our context. So over here, we have our Lambda code, which is all in the TypeScript, JavaScript world. So it's all about objects. Whereas over here, we're in the DynamoDB world, and its data types are specific to DynamoDB. It has its own native data types. So we've got to transfer from one data type world to another world. And that's what's called marshalling and unmarshalling. So whereas over here, we might have objects, and we want those to be marshaled into the corresponding types that DynamoDB understands. And the same is true on the other side. When we try to read something from DynamoDB, they're going to be in the native DynamoDB types here, and they have to be unmarshaled before they can be presented to our JavaScript code. Now, clearly, we don't want to be bothered with all of that nitty-gritty of marshalling and unmarshalling, and that functionality is built into the DynamoDB SDK, although we do have to tell our DynamoDB client the type of marshalling that it should do. So it seems like that there are a couple of options available to us, which we won't be getting into. We will be using the same marshalling and unmarshalling options every time. So it's effectively boilerplate code, but we do have to tell our document client every time we use it in every Lambda function, the marshalling and unmarshalling options that we would want it to use. Okay, all of this stuff gets hopefully makes a bit more sense when you start playing around with it. So in the previous slide, I'm showing you essentially an example of a single item action. If I go back yet again to, okay, I've just demonstrated a single item, how we program a single item action. And in this case, it was just a get, but the puts and the updates and deletes are not too dissimilar. What about a query action where we want to get a collection of items? And we know now that we can only perform queries on a table that has a composite primary key, combination of a partition key and a sort key. So I'm reiterating that point here, that you can only query on the basis of your partition key, sort key combination. You can't query on the basis of other attributes associated with an item. If you do want to do some filtering based on these attributes over here, you have to do that filtering within your kind of Lambda code, if you like. So so I'm saying a query returns items based on the partition key. Oh yeah. So when we are programming our query, we have to specify the partition key, and we've got to give the exact value of the partition key. So it's going to be, it has to be, it's an equals operator statement of the partition key value. You can't specify kind of an upper limit or lower limit or anything like that. However, for the sort key part, because you have to specify the full primary key, the partition key part has to be a single value, i.e. the equals operator. The sort key part, though, can be a range of values. So you can use things like less than or equal to, greater than or equal to. Now, obviously, these only make sense if the sort key's type is a number type. You can as well have the sort key as a single value. But if you're going to do that, then you may as well use a single item approach rather than a query approach. But so you can specify, you can use these operators in your expression of the sort keys that you're interested in, the sort key values that you're interested in retrieving from the query. Or if the sort key is a string, then you can specify a begins with operation on it. So you're only interested in a collection of items that have a specific partition key value, but the sort key begins with ABC. Okay, just off the top of my head. So that's obviously going to return potentially. This is going to return a number of items, i.e. a collection. You can also specify filtering, but the filtering is done on the client side. But you can express in your SDK code, you can express filtering criteria, and the SDK will actually carry out the filtering for you, but it'll only do it on the data that it has retrieved across the network from DynamoDB. The DynamoDB service itself on the server side, it ignores this filtering. It doesn't know how to interpret it. There are some limits on the size or the amount of data that can be returned from a query request, and we're saying it can be up to 1 megabytes, or the number of oh yeah, you can, if you know that a query could return a large number of items and you want to try and limit it because those items have to travel across the network and maybe you're concerned about latency, if you want to limit the number of items that are returned in the collection, then you can specify a limit in the query request. And because remember, the collection of items that come back from the query, they are going to be sorted in the order based on the sort key. And so if you specify a limit in your query request, then it'll take, the top number within that collection. The DynamoDB is able to do that on the server side. It also supports pagination, although we won't get into that. Here's an example, and you won't see this example in the lab that you're working on at the moment, but you will see it in a subsequent lab. So the idea here is I've got this table that contains information about actors that have played a role in a particular movie. Okay, so I've got a table that has loads of movies information in there, but we're storing the various actors in each movie and the role they played in that movie and other information about that particular role, let's say. So for this particular table, I have my partition key is a compound key. My primary key is a compound. It's made up of a partition key and a sort key. The partition key I've decided is going to be movie ID again. But the sort key, I've just arbitrarily chosen actor name. Now, don't worry whether you think that's a good idea or not, but I've just said actor name is going to be this sort key. And clearly, same actor is going to appear in many movies, but that's fine. The combination of actor name and movie ID is going to be unique for each item in this table, and hence it qualifies as a primary key. And the rest then is as before. And my actor name is of type string and my movie ID is of type number. That's fine. Down here, then, I'm showing you an example of carrying out a query request against this table. I've left out the instantiating my client now. We've seen that code before. So I have my document client here. And again, I'm just invoking the send method on it. And in this case, the kind of command I'm sending it is a query command. And here's the properties that I need to specify in my query. What table am I querying? I need to specify, okay, so here is how I express, if you like, the collection that I'm looking for. So you express it as a statement like this. This is a bit like a where clause in the SQL world. So I'm saying I'm only interested in movies where the movie ID is equal to a specific value. This is just a placeholder or a variable name, if you like, in this overall expression. But note I'm using the equals operator. It has to be the equals operator. That's the only option I have for the partition key part. I mentioned that on the previous slide. So I'm only interested in this collection that I want returned. The movie ID has to be a specific value. And I'm saying the actor name has to begin with a specific substring. Now, I'm saying that :m here is a variable and :n is a variable. Where do they get their actual values from? Well, I'm expressing that down here. And this is just the way the query command is designed. So we have to live with that. So it looks like I'm only interested in the movie whose ID is 1234, and I'm only interested in the actors in that movie whose name begins with Bob. Yeah. So that's an example of a query request to our table. And as we said on the few slides back, you can only perform query requests on tables that have a composite primary key, which our movies cast table does. The request has to be for a specific partition key, which is the case in we're honoring that. Our movie ID is a specific value, whereas the sort key can be expressed as a range. And because my sort key is a string in this case, the only ranging option I have available to me is this begins with. option. I don't have anything else. I can't have, let's say, contains, that the string contains a particular substring. The DynamoDB designers just don't give us that option, I guess. Okay, I'm going to leave it at this point, and we'll pick up the story on DynamoDB in the next lecture. Thanks.